Lecture 10: The design of two-way slabs. Let's do an example. A rectangular reinforced concrete slab for a hospital of plan dimensions 5 meters by 3 meters and a thickness of 150 millimeters is simply supported on all four sides. Screed of 50 millimeters will be applied on the finished structural concrete. The concrete class is C2025. A cover of 25 millimeters is to be provided. Assume T12 bars, provide the steel reinforcement for the slab and check the deflection. The first step we'll want to do is to check whether the slab is one-way or two-way spanning. Next, we'll check the ultimate load on the slab, then determine the ultimate moment capacity of our concrete section. Then, using the moment coefficient table, we will determine the major moment, that is the moment in the short span, and the minor moment, the moment in the long span. After that, we'll provide the reinforcement for the slab in the minor and major direction. And lastly, we'll check the deflection of the slab on the major direction only. So that's the question. There is important information we need to read off from our handout. One will be the live load of the hospital, which has been given as 2 kilonewton per meter squared. Next, we'll need to know the density of concrete, which is 24 kilonewton per meter cubic. Then we'll get the longer dimension Ly, which is equals to 5 meters, and the shorter dimension 3 meters. We will do Ly over Lx and get 5 over 3 is equals to 1.67, which is less than 2. Therefore, our slab is two-way. We will then compute the permanent actions. We will compute the self-weight of the slab, which will be 150 millimeters converted to meters to be 0.15, and the density of reinforced concrete, which is 25. Then we'll get the density of screed, which is usually just plain concrete, which we have been told in the question is 50 millimeters. So convert 50 millimeters to meters multiplied by the density of concrete, 24. Total that up and our total dead load is 4.95. Our variable action of the hospital will be 2, and our corresponding total variable actions on the slab is 2. Then we'll get the design load eta, which is equals to 1.35 GK plus 1.5 QK to get 9.68 kilonewton per meter squared. We will then calculate the effective depth D by taking the overall depth minus the cover minus half the main bar diameter, which we will assume the main bar diameter for now is 12. We will get our effective depth is 119. Slabs in residential buildings do not have shear reinforcement, hence the diameter of the link is not subtracted like in beams. The design moment of resistance, MRD, is then calculated using that formula to get 47.3 kilonewton meter. To get the moment effect of the design load, we will need our table, our moment coefficients table. And to do that, we will need to get our ratio of Ly over Lx, which is 1.67. The table provided does not have the value of 1.67. However, we can interpolate between 1.5 and 1.67. To do that, we will need a reminder on some Cartesian coordinate system in which we have a y-axis and an x-axis. And if we have the value of 1.5 at that point, whose value here in the y system is, the y coordinate system is about 0.104, and we have the value of 1.75 given here as 0.113. If we assume the two lines are linked together by a straight line, then we can interpolate the value of 1.67 there by computing it as follows. We will read off the value of 1.5, the y value of 1.5, which is 0.104, and then we'll take the gradient between 1.75 and 1.5, so that's the change in y, and on the denominator the change in x, multiplied by the difference between 1.67 and 1.5 to get the value here of 1.67 is around 0.110. The same can be repeated for alpha sy, and you'll get the value of alpha sy is 0.0399. So to get the major moment then, it will be msx is equals to alpha sx eta lx squared to get 9.58 kilonewton meter, and msy, we will do alpha sy eta lx squared to get 3.479 kilonewton meter. For the major moment or the short span, we'll have the moment effect of the design load as 9.58 kilonewton meter. We'll compare that with the design moment of resistance, and we will get that it's singly reinforced. Similarly, we could calculate K and get that it's less than K prime. We'll then go ahead and get Z, which is 0.97. However, it's good practice to limit Z to be not greater than 0.95 D. We'll then calculate the area of steel, and you'll find that is 212 millimeters squared per meter. We'll then compare the 212 millimeters squared per meter with the minimum area requirement as stated in the Eurocode, which is given as 0.13% BD. We'll compute the values and get 155 millimeters squared per meter, and 155 millimeters squared per meter is less than what was required, 212. So we provide for the larger of the two, which is 212 millimeters squared per meter. We go ahead and read this off from our reinforcement table, that is table 2. It has the areas of steel in millimeters squared per meter. We provide anything larger than 212, of which T8 at 200 bottom 1 gives us this value, and T10 at 300 bottom 1 gives us 262 millimeters squared per meter. Either of the two are right answers. Ideally, you should always be providing one. The minor direction, for now we can see maybe we decided to use T8 at 200 bottom 1, which gave us 252 millimeters squared per meter. So let's assume we went ahead with that. So since we have determined the diameter of the main bar as 8, we can assume the diameter of the secondary bar will not be greater than 8, and just assume 8. So we need to calculate the effective depth in this orthogonal direction. In this case, we will take 150 minus the cover minus the diameter of the main bar, minus half the diameter of the secondary bar. That gives us 113. We'll calculate the design moment of resistance, which is 42.65, and this is less than MSY, which was 3.47 kilonewton meter, and therefore our slab is singly reinforced in the minor direction as well. We'll go ahead and calculate K, compare it with K prime, find it singly reinforced, get the lever arm, which is in this case is 0.988 D. It's good practice to limit the lever arm to 0.95 D. Get the area of steel. Now our lever arm was 0.95 D. We get our area of steel is 80 millimeters squared per meter. We'll then compare 80 millimeters squared per meter with the minimum area of steel requirement as per the Eurocode. So AS mean in this case gives us 147 millimeters squared per meter. So the area of steel required was 80, but the minimum is 147 millimeters squared per meter. So provide the larger of the two, which in this case happens to be 147 millimeters squared per meter. So we will provide for this area of steel. And when we refer to our reinforcement table, table 2 to be specific, then we will get T8 at 300 bottom 2 satisfies this condition. So 168 millimeters squared per meter. Then we could provide a sketch maybe. So if this was our slab, I'll do a rough sketch. We'll have the longer direction. And we'll need to provide steel in the major direction. So in this case, we have this thick bar. So I'll choose to represent it. Of course, there are many other bars like that. Here, here, here. Every 200. But that will make our sketch very hard to interpret. So we'll instead rub off these lines. Instead of doing that, we will take a leader and annotate this bar here, which I've said is T8 at 200 bottom 1, gives us 252 millimeters squared per meter. Then we'll go to the other direction. And choose the secondary bar. So we will say that this bar here, even though I'm drawing one bar, there is a bar every 300 millimeters from that one. So that gives us T8 at 300 bottom 2, which gives us 168 millimeters squared per meter. So that's how a sketch would be before it's taken to the detailer. This will be the sketch from your calculations, which will be used by the detailer to make the detailed structural drawing. So after this, we need to do ideally other additional checks. We could do shear, but that's not usually critical in the design of slabs. Instead, we'll go to the design or the verification for deflection. As stated previously, the deflection verification consists of two equations, equation A and equation B, and this circled criteria determines whether we'll use equation A or equation B. So first, we'll need our reference reinforcement ratio, rho naught, which is given by that formula. This is usually provided to you in a supplementary handout. Then you also need to get rho, the reinforcement ratio. This was the area of steel required in the major direction. Remember, we only check for deflection in the major direction. We'll then compare rho with rho naught. In this case, rho, which gives you this, is less than the reference reinforcement ratio, so use equation A, which is what we'll expect. Most of the time, we end up using equation A for slabs, and most of the time we'll end up using equation B for beams. But always remember, that's just say a rule of thumb, and it does not always happen that way. You always need to do this check to know whether exactly you need equation A or equation B. Since we have equation A, we need to populate these values in equation A. So since the slab is simply supported, then K equals 1. And since it's singly reinforced, we don't need rho prime since there's no compression reinforcement. We'll then calculate F1. So F1 is given by this formula. We need S required, which was 212. However, we provided something larger than 212. We provided T8 at 200, which gave us 252 millimeters squared per meter. And so we find our value of F1 is 1.29. Next, we'll fill in and replace these figures to get our span to depth limit that the code allows is 77.57. However, an additional requirement is that this limit should never exceed 40. So we will use the limit of our span to depth as 40. We'll then go ahead and calculate our span, our actual span to depth ratio, which will be 3000, the shorter span Lx, over the depth 119, to get 25.21. And since 25.21 is less than the limit of 40, then you can say this slab is adequate in deflection. Then since this is accurate, then if you had not sketched it before you checked deflection, this is the point where you will include the sketch, the final sketch. Let's do another example. The question reads, a rectangular reinforced concrete slab for Arkham Asylum of plan dimensions 5 by 3 meters and a thickness of 5 millimeters is simply supported on all four sides and restrained by beams. Screed of 50 millimeters will be applied on the finished structural concrete. The concrete class is C2025. A cover of 25 millimeters is to be provided. Assume T12 bars. Provide the steel reinforcement for the slab and check deflections. This question is similar to the past one. Some little trick, maybe we'll just to note that an asylum is something or sort of a hospital. And the live loads for this is similar as the last example. An addition, just highlighted here, is that this slab is now restrained by beams. The procedure will follow the last example. We'll establish if this is a one-way or two-way spanning slab. We will determine the ultimate load on the slab, get the ultimate moment capacity, Then we'll use the moment coefficient table to determine the major and minor moments, then provide the reinforcement for the slab in the minor and major directions. Then we'll verify that the deflection of the slab is below the limit provided. There goes the question again. We need the density of concrete and also the live load of the hospital, which is 2. We'll start with our longer dimension, Ly, which is 5, our shorter dimension, Lx, which is 3. Ly over Lx gives us 1.67, which is less than 2, therefore this is a 2-way slab. We will calculate the permanent actions from the fell foot of the slab and an additional screed of 50 millimeters. We would add that up to get the total dead load as 4.95 and read off the value of our occupancy load for hospital, which is 2, to get Qk is equals to 2. We'll then get our design load eta as 9.68 kilonewton per meter squared, exactly the same as the previous example. Then we'll calculate the effective depth D by taking the overall depth less the cover less half the main bar diameter to get 119. The diameter of the link is ignored as there are no shear links in slabs or residential buildings. Computing the design moment of resistance MRD will give us 47.3, and we will need to get the values of in this case now beta Sx and beta Sy, since we have beam restraints. There's not an exact value of 1.67 in the table as shown in this chart, so we will need to interpolate between 1.5 and 1.7. Next, we'll also need to know what type of panel is it. So as discussed in lecture 9, this will have 4 edges discontinuous, and we'll have to interpolate between 1.5 and 1.75 in this process to get beta Sx as 0.09948. Beta Sy in the case of beam restraints does not need interpolation, and we will therefore read the value of Ly of Lx directly, which is 0.056. So to get the value of the major moment Msx, that will be beta Sx eta Lx squared, and that will give us 8.67 kilonewton meter. And in the minor moment, Msy will give us beta Sy eta Lx squared to get 4.88 kilonewton meter. We'll then go ahead to calculate the flexural reinforcement for the major moment, which will give us that the moment effect of the design load is less than MRD, that's singly reinforced. We'll calculate K and get that K is less than K prime, so singly reinforced. May seem like repetition to get the value of K, however, we always need the value of K in order to determine the lever arm Z. So Z in our case would end up being 0.972D, so we have to limit Z to 0.95D when we are computing the area of steel, and that will lead us to get AS as 192 millimeters squared per meter. We'll then compare this with the minimum area of steel as stated in the Eurocode, and we'll find that 192 is greater than 155, so we provide for 192, and to provide we'll need our table 2. So we provide anything larger than 192, so T8 at 250 bottom 1 gives us 201, and T10 at 300 bottom 1 gives us 262. Any of these are right answers. Of course, you need to keep both the value you decide at the back of your mind, because we will need this value while we are going ahead to calculate or to verify deflection at the later stage. For the minor moment, we will need to get the flexural reinforcement as well. But since we assumed in the other case that we had T8 at 250 bottom 1, that gave us 201 millimeters squared per meter. Well, now since if the main one had 8 and it's usually the stiffer side that has most load, then it's highly unlikely you'll get a higher area of steel or higher or bigger diameter bars in the other direction. So since we already have the main as 8, it will be wise to assume the secondary diameter bars having a maximum of 8 as well. So we will calculate the effective depth in the other direction, which will give us 113. Then the design moment of resistance is 42.65, and comparing it with MSX gives us the conclusion that this slab is singly reinforced in the other direction as well, which is expected. So K gives us 0.0191, less than K prime. We need the K to get the value of the lever arm, which we input there. Together Z is 0.983D. So we limit Z to not greater than 0.95D, as that is good practice, and we'll get the area of steel is 144 millimeters squared per meter in the other direction. Compare this with the minimum requirement as mean, and we find that 114 is less than 147, so we provide for the greater of the two, which in this case happens to be AS mean, so provide for 147. So 147 millimeters squared from table 2, we get T8 at 300 bottom 2 gives us something more. 168 is more than 147, so we can go ahead with T8 at 300 bottom 2. As usual, you can provide a sketch of that point, or you could go ahead and first verify deflection before you sketch, which is what we'll do this time around. We'll get the span of a depth limit as allowed in the Eurocode, can either be equation A or equation B. The criteria that will guide us in using whether equation A or B is this part. Our reference reinforcement ratio in our case is root FCK multiplied by 10 to the power of -3, which gives us 0.00477. Our reinforcement ratio is the area of steel that was required, which was 192 millimeters squared per meter, even though we went ahead and provided T8 at 250, which gave us 201 millimeters squared per meter. So we'll still need the 2, but for now we just need 192, which gives us 0.00161. So rho, the reinforcement ratio, is less than the reference reinforcement ratio, so that implies we use equation A, which is what we sort of expect, because we end up using equation A a lot of times in the design of slabs. Then we need to compute the limit allowable as per our code of the span to depth. We'll use the worst case, that K equals 1, since it's simply supported, even though it's simply supported by restraining beams. We'll find rho prime is 0, since there is no compression reinforcement. F1 is given as that. We required 192 millimeter squared provided, millimeter squared per meter, even though we provided 201 millimeter squared per meter. That's there. It goes ahead and does that, and we find that F1 is 1.138. We replace all these values in equation A. We find that the limit of the span to depth is 70.22, but the code stipulates we should not allow that to exceed 40. So we compare it with our actual span to depth, which is 3000 over 119, get 25.21. And since that is less than 40, then our slab is adequate in deflection. Then this, after verifying, is now the point where we could sketch our areas of steel. So that's our slab. I will have the main bar running in that sort of direction. There are many, but I want to make something easier for the structural detailer to follow. We'll have that. And we'll see that this bar over here runs from that edge all the way to the edge of this slab, and that gives us T8 at 250 bottom 1, which gives us 201 millimeter squared per meter. And in this other direction, we have this bar running in the minor direction, and in that case we see that this bar that you're now circling runs from this edge all the way to this edge, and that gives us T8 at 300 bottom 2, which gives us 168 millimeters squared per meter. So that will be the answer. We could have a few more notes on stair design. So there are key terms we need to know in the design of stairs. One is the riser, which is that point over there. The next is the going. So the going is usually the nosing plus the tread. The tread is the overall distance. We usually have this notch called the nosing and the going. We also have the slope here, which should generally be around 30 degrees, though that's usually advised by the architect. And we have the waist, H. This is usually the structural component of the stair. The component that provides structural resistance to the weight of the stair. The dimensions of the stair should be such as to give the maximum comfort to the users, which depends on the use of the buildings. Generally, risers should be approximately 150 to 175 millimeters. The going varies between 200 millimeters to 400 millimeters. In practice, the riser and the going can be proportioned according to this formula. 2R plus G will be less than or equal to 600. So 2 risers plus 1 going should always be less than or equal to 600. There are various types of stairs: straight stairs, freestanding stairs, helical stairs, spiral stairs, slabless stairs, and so on. Straight stairs are shown in this manner when all the flight of stairs is supported on the edges of the stair such that the load is transferred in that manner. We see this stair is spanning longitudinal. When each stair is supported directly such that the load in this case is being transferred by each stair, then we see the stair is spanning transversely or horizontally. These are examples of straight stairs. This is a straight stair at the University of Nairobi Tower. We have other examples of straight stairs. This is in Civil Block, University of Nairobi. This is a straight stair in the Engineering Block, also at the University of Nairobi. We also have freestanding stairs and helical stairs. These stairs usually look appealing since they have the illusion of floating, since there is no support here. Is a helical stair. No support between that point and that point. It has the illusion of floating and is usually aesthetically pleasing, but may end up being quite expensive. Then we have spiral stairs, which is similar to helical stairs. However, most of the support comes from the central column in the staircase. This is an example of the spiral staircase. An example can be found on the concrete laboratory, University of Nairobi. We also have slabless stairs in which there is no definite waist. This is an example of a slabless stair under construction. These freestanding and slabless staircases end up being a bit more expensive than conventional straight stairs.